sort of give it some time here. So the basic idea is, so this is 1C number 5? 1B number 5. Okay. So the idea says, so what the exercise says, and the language of the exercise I think is a little bit, vague. Because what it says is show that you can replace the property of every element having an additive inverse with the property that 0v is equal to 0 for every vector v, right? And if you remember in the book, it actually proves it in the forward direction. So the book contains the proposition. There's a proposition in the book that says that if you're in a vector space, I'm going to put it in like plain if then language here. What it says in the book essentially is the statement: if every v has a unique additive inverse, then 0v is equal to 0 for all v. That's what the book proves. The book actually just says this, that 0v is equal to 0 for all v, but the way it does it is it assumes this property and then uses it in the proof. So the book's version of it is the forward direction. It says, if you knew everything had an additive inverse, then 0v is equal to 0 for all v. What the homework exercise is asking you to do is to reverse that argument. The homework exercise wants you to establish that if 0v is equal to 0 for all v, then every v in v has a unique additive inverse. So it's asking you to reverse the logic of the statement. Don't assume the additive inverse statement. Assume that this 0 property holds, and then force the additive inverse to exist. Okay? So does anybody have any idea how to get started on that? What do you do? What's the basic idea? Yeah. Yeah. So how, I mean, so like, suppose you just write that down. What are you going to do with it?
I did it. Zero, scalar 0 equal 1
Cool.
vector space.
Okay.
Property works. Probably it's a negative.
So the uniqueness comes from the fact that if they were different, there's a unique 0 vector. That's really that's how you're going to get the uniqueness of the additive inverse would come from the 0 vector. But this is the basic idea here, right? Is that you're notice in a lot of ways, this is literally the reverse of the argument that the book made in the forward direction. It's the same equations, even just in the opposite order. Right? Yep.
Why does there have to be a forward and backward direction of this? I mean, if
Because
one equation is equal to another, are they not the same statement?
No, because when you're laying out definitions, when you're axiomatizing an idea, right? So when you're making the axiom statements of what a vector space is, you're setting up the definition. You start with a set of statements that you assert to be true, and then you derive all the rest of them.
Yeah.
Right. So what this is saying is somewhere in the if we say V is a vector space, if, and then somewhere in that list of ifs that it has to satisfy is the statement there exists a W such that V plus W is equal to 0 for all V in V. That's an axiom that you stated as part of the list of properties that the vector space holds, right? And if you can prove that these are equivalent statements, what you're saying is you could have chosen this to be the axiom instead. Mm-hmm. And that this would have been derived from that. That these are equivalent. This is a normal game that you play when you're setting up axioms, is what's the least you can start with? Well, you can have your choice. You can start with this and prove that, or you can start with this and prove this. I mean, that's what the point of this. I'm not sure exactly why he couched it in that language, but the point is prove that this is an equivalence and not an implication. Okay. But by equivalence, I mean like an if and only statement. So he's saying he could have, in plain language, he could have said, prove 0v is equal to 0 for all v and v if and only if there exists a W so that v plus W is equal to 0 for all v and v.
That's the plainest language version of what he said that you could write. Okay, and he's using the language of in the definition, or because he's trying to point you to the idea, sort of a higher math idea, that when we select axioms, we have choices about how we axiomatize an object. Okay. He often, this will not be the first time he asks a question that is much simpler than it appears. So if you get confused about stuff like that, let me know. Okay. All right, anything else? Yep.
So just in general, when we're writing proofs for our homework, like one of the questions was to prove that the negative of negative b is equal to b. One of the propositions in 1b was that negative b is equal to negative b, or like negative times b is equal
Sure.
to negative b. Are we allowed to, in our proofs, say like by propositions?
Yes.
Kind of assume those even if we have.
Yes, so there's a couple of different ways. Yeah, so you actually should be like, if you make an assertion about a statement, especially in the beginning when we're sort of getting started and like building up the machinery, you should cite why things are true. So if you write down something like, okay, so what are you trying to show, that minus b is equal to b? Okay, well, one way of saying that would be, so here's what I would do, right? At least the skeleton of the way I would approach this. So what you said is that the book says that minus, oh, okay, there's absolutely a route through what you're taking, because what you would say is, okay, well, that's just a vector. And the proposition says that minus b, that minus b is equal to -1 times minus b. That's what that proposition would say. Oh, but also that same proposition says that this is true, right? So but you'd have to cite in both cases that you're using that you should cite that you're using that proposition. Later on, it won't be so important if you cite basic stuff like that, but at the beginning, when we're not working with very much, you should tell me why you're making the move. Yeah, I mean, I'm at the board, so I can write lazy stuff like by proposition, what is the number, whatever it is, by proposition, whatever, and I could say by prop, whatever. But you guys are practicing mathematical writing, so you would have a paragraph where you said by proposition 1.35 minus b is equal to -1 times b, and again -1 applied again, -1 times b is equal to -1 times b. Or honestly, if you wrote this out as an equality and you said, like, so Axler does this all the time, well, he'll lay out an equality, he'll tell you the first equality follows by proposition this, and the second equality also follows by proposition that. In either case, you're correct in the way you write. Yeah, so like it's one of the hardest things about this class is using a little freedom when you're laying these proofs out, but staying within whatever the constraints of rigor, right? It's sort of a hard balance to take. I mean, I'm not gonna jam you up if you prove something like this. You lay out an equality, and underneath, you put a little star on it. And next to the star, it says by proposition 1.35, also acceptable. Right? However you want to arrange it, just so it's readable and clear what the logic is. Anything else? Yep. Which one was that one? Just remind me what the statement is.
I think it was like, suppose A is an element of the field, B is an element of capital V, and A, B is equal to 0. Prove that A equals 0 or B equals 0.
Oh, okay. So that's this one where you have like A is in F and B is in B and AV is 0. Prove A is equal to 0 or B is equal to 0, where here you have to deal with the fact that the same these are two different zeros, right? That's the scalar 0 and that's the vector 0. Okay, so this is actually a really common proof structure in this class and others, which is if it's an either or type setup, you can dispense with one of the cases basically immediately. If it happened to be the case, so you've assumed that AV is 0, right? If A was equal to 0, we would be done. So if this was true and A was 0, there'd be nothing to prove, right? So assume A is not equal to 0. That's the game, right? So the logical structure of an argument like this is cut one of the cases off. There's only two possibilities, either A is 0 or A is not 0. If A was 0, you'd be trivially done, right? If A was 0, you would have proved it. Well, look, there it is. If A was 0, A is 0. So assume A is not 0 and try to show that if A is not 0, that forces V to be 0. So what we're going to do is show that V is equal to 0, using the fact that A isn't 0. Now, there's a really awesome thing. This is the last hint I'll give on this one, so I'm not walking through the solutions before you guys have had a chance to finish them up. What can we say about a scalar A if it's not 0? Yep. Has a multiplicative inverse, right? If A isn't 0, then if A is not 0, 1 over A exists. And you should use that fact. That's all you need actually to do this problem, is the fact that if A is not 0, it has a multiplicative inverse.
What if I just like quoted a proposition?
If you quoted it correctly,
I don't know.
well, why don't you stick around and show me what you did after class, all right?
Okay.
Like, I'd be curious to see how you did it. I mean, certainly it's the case that you can quote propositions. I will tell you there's a blanket prohibition on quoting propositions from ahead of where we are in the book, which I'm assuming is not what you did, but yeah, just like putting it out there that if you can find some far future theorem that implies the homework question, you can't say, oh, by theorem 2 in chapter 5, this must have been true. Like, okay, I mean, yes, but we have to build there. So like, that's actually a good, what are you allowed to just assume is true? So I should mention that before we go on, which is you're allowed to assume the theorems of calculus. So one of the questions that was in here was about like, how do we deal with continuous functions, like showing that continuous functions are a subspace? What am I allowed, what am I going to allow you to say? If you want to say that the sum of continuous functions is continuous, that's like in chapter 1.1 of like any calculus book, is that the sum of continuous functions is a continuous function. Just say it. Now you have to say the sum of continuous functions is continuous, but you don't need to prove it. In fact, if you do, like, I'll be impressed, but you know, like epsilon delta proof or F preserves all convergent sequences, like, don't do that. Just say it. It's okay. And if there's a question about whether or not you're allowed to assert something from a different course, ask me so I can just tell you. Okay. The differentiable functions are closed under addition. You can just assume that the sum of differentiable functions is differentiable. Find that in a calculus book. Okay. All right, anything else before we go on? Okay. So let us talk about this week's stuff. So we're going to talk about how we glue subspaces together into new subspaces and how that fails in some way. So I guess the first thing I want to point out here is that normally in the past, in your mathematical past, especially if you're just out of 248, you probably have the idea that the way you build new sets out of old ones is you just union them, right? If you had two sets and you want to make a new set that includes them both, you just union them together, right? Oh, I've got U and I have V. If we take the union, it's just all the elements. I mean, to be in the union means that you're in one piece or the other piece, right? If U is in U union V, then U is in U, or U is in V. Now that's not a very strong condition when we're talking about vector spaces, because imagine that now we've got U and V are subspaces, and I want to glue them together in some way that makes a new subspace. This is a thing we do all the time in mathematics. I can't do this with unions. And here's a really easy explanation of why. Okay, so I'm in R2 and I have this line right here. So line 1, well, it's a subspace. Lines in R2 are subspaces, right? If you take a subspace and you add it to a vector of two vectors in your atom, you stay in the same line. If you stretch them by a vector, they stay in the same line. Now take another line in here. Okay, well, here's a different line. L2, also a subspace. If you union those together, all you're saying is, oh, well, the union of those two lines is this line and that one. That's it. That's all the vectors, right? All the vectors in this line and all the vectors in that line. So if you were going to say that this together was a subspace, I mean, this is a homework question, so I don't want to totally give it away, but why isn't U1 union with V? Why is this not a subspace? Like what fails? Yeah, right. So you guys both have the same answer, right? If you take two vectors in here and you add them together, you don't land in the same space, right? If you took this vector, which is in line 2, and you took that vector, which is in line 1, and you add them together, you end up out here. But that vector is not in either this line or that one, right? Say either this line nor that one. So it's not closed under addition if you need it. Union is a bad tool for making new subspaces because it's not closed under addition. Well, that sucks. It means we have to have like a better tool. Unions are awesome, but they just don't carry enough information. So what we're going to do instead is we're going to define what it means to be the sum of subspaces. And so we're going to start with a definition of the sum of subsets. And then we'll show that this is the correct idea for lifting up to making new subspaces out of old ones. I don't know why I'm using more. All right, so suppose that we just have subsets U1 through UM, subsets of, say, V. Sum one two is elements, or I guess the set with elements of a form U1 plus U2 plus UM. So it's just pick one from U1 and one from U2 and one from U3 and one from U4 all the way to UM and then just add them all together. Where Uj is in Uj, or J is equal to 1. And pick one pile, one from this pile, one from that pile, one from this pile, one from that pile, and then just add them all together. And we denote such a set. So sum UM is denoted. Probably shocking that we use a plus sign. That's it. If I'm adding the elements of sets together, this is what I mean. Now notice, there is no subspace structure here. I'm literally just saying, you give me some sets, I construct the set sum by just adding them together, adding the bits together in all possible ways. As an example, if you like, if U1 was equal to 0, 1, U2 was equal to, say, 2, 3, and U1 plus U2 is just all the possible combinations of things from this set added to things from that one. 0 plus 2, 0 plus 3, 1 plus 2, 3 plus 3. That's all it is. Everything you get by gluing together.
Very different from like vector addition.
So what we're going to do is we're going to impose vector condition on this, right? So it's the addition, the set addition is not like vector addition. Where the vector addition is going to come in is right here. When we start adding the elements together, when we glue vector spaces together, this addition will be vector addition at this level. Okay. Okay. So I just want you to think of this as an operation on sets. Okay. So here's another one. If you had U1, and this is another example here. If U1 was equal to everything of the form x, 0, 0, where x is in a field, And U2 was equal to everything of the form 0, y 0. Y is in the field. Those are subsets of R, right? Of R3. Then U1 plus U2 is equal to the set of things that look like X, Y, 0, where X and Y are in the field, yeah? It's everything that looks like this plus everything that looks like that. So the set of possible objects that comes out looks like, well, free choice in the first slot, free choice in the second slot. What's that?
Why is the last element of one plus E2 6?
Because I'm an idiot. Does that make you better? Good question. I haven't reinvented the rules of arithmetic, although I've tried occasionally.
Okay, so it's the same basic idea here. You have two sets. This is the pattern that describes their elements. So if you want to describe what their sum looks like, well, it must be things of the form X, anything of the form X 0, 0, plus anything of the form 0, Y 0. Oh, Jesus, that's terrible. X 0, 0 plus 0, Y 0 must be of the form X, Y 0. That's where the vector addition comes in. Okay, notice I've not at all referred to subspaces yet, just set operations. I'm constructing new sets out of old ones by every possible sum combination of their elements. Okay, so now this is where we get the good property that this has, which is some proposition. If U1 and U2 are subspaces of the, so is U1 plus U2. So if you start with subspaces and you take their sum, you get a subspace back out the other side. So the standard thing we have to do when we assert that something is a subspace is we have to show the three properties. Now, it is important, I got asked this question in office hours. Let me just, as strongly as possible, tell you that when you are, like, the way to success in this class is knowing your definitions. There's going to be a timed exam in here at some point. You're going to have to deal with doing proofs that are constructed to be doable in a 50-minute period. But if you don't know your definitions and basic structural theorems, you're going to have a hard time with that. So your theorems, your theorems, your basic theorems and your definitions have to basically be on immediate command. So if I say to you, one of the most common things we're going to do in this class is prove something is a subspace, everybody in here should know exactly what I mean by that. How do I prove something is a subspace? Additive identity, closed under addition, closed under scalar multiplication. That has to be instant, okay? Because say you get a problem like this on an exam and it says prove it's a subspace, I'm telling you what to do, right? I'm telling you what the format of the argument is. So let's do that. Step one is, well, okay, 0 is in U1 plus U2. How do I know? Well, is 0 a sum of something in U1 and something in U2? Sure, because 0 is in U1 and 0 is in U2. So 0 plus 0 is in plus. Why is 0 in U1 and U2? They're subspaces, right? So it's kind of a two-way door. On the one hand, 0 is in these guys, and so therefore the sum must be in the sum. Okay, step 2. This is the easy part of this. I'm taking a proposition of the book and I'm cutting 2 pieces. Step 2, additive, closed under addition. Step 2. Okay. The basic format for closure under addition is assume 2 different elements in the set that you're working with. So let's let U plus V be an element of U1 plus U2, and also U prime plus V prime be an element of U1 plus U2. They have that form because anything in the sum has U and U prime in U1 and V prime in U2. That's what it means to belong to the set sum, right? Is that you have a piece that comes from the first set and a piece that comes from the second set added together. So if you select a random element from this, this is what it looks like where U is in U and V1 and V is in U2. If you select another random element to add it to, you've got another random element in the same set sum. That's again in U, that's again in V, okay? So what we want to show, totally okay to do this, by the way, to give yourself sort of structural hints about where it was you're going so you don't get lost. So WTS or want to show, what is the thing that we want to do? We want to show that U plus V plus U prime plus V prime is in U1 plus U2. That's what we're after. That would show closure of addition if that sum was in there. You don't need to do this. I'm putting it in here as a hint about future structure. So just do it. Well, associativity would say that this is U plus U prime plus V plus V prime. What can I say about U plus U prime? Well, it's in U because U1, I'm sorry, this is in U1 because U1 is a subspace and therefore closed under addition. But U plus U prime is in U1 and V plus V prime is in U2 as subspaces. But if you've got an element that's combined from a piece from U1 plus a piece from U2, that's precisely what you mean about being in the sum. So U plus V prime plus V plus V prime is in U1 plus. Has the right form. Something in U1, something in U2. It's got the right structure. It's in the space. Therefore, it's closed under addition. Make sense? Yep.
Can you re-explain the first two sentences, like why U and U primes in U1?
So when you're trying to show a closure for a generic subspace argument like this, if I'm trying to show that this set is contained, that this thing is closed under addition, right? What I want to do is I want to say, okay, let's let, I don't know, X be an element of U1 plus U2. There's one element in it. And let Y also be an element of U1 plus U2. But I can say more. I want to say, okay, pick a random element and another random element and add them together, right? Show that X plus Y is an element of U1 plus U2. But I can say more than just X and Y because I know what the structure of everything that's in here has this form. Everything in the set sum must have a piece that came from part one and a piece that came from part two added together. So what I'm doing here is I'm saying, okay, I picked random elements, two random elements from the space, but they must be able to be written like this because they're set sums. Right? Anything in a set sum has to have that structure. Otherwise, it wouldn't be a set sum.
So U little U is from U1.
Yeah, this piece right here, this is the part that came from U1, and these guys came from U2. It's like we've got pieces that are living over here acting like U1 bits and pieces that are over here acting like U2 bits. We're taking advantage of the fact that U1 and U2 are subspaces. Okay, so the argument for closed under scalar multiplication is very similar. So for scalar multiplication, the standard structure of a subspace argument is to assume that you have an arbitrary scalar element. So assume that A is an arbitrary element of the field, and that U plus B is an arbitrary element of U1 plus U2. Again, where U is in U1 and B is in U2. Okay. What we want to show is that A times U plus V is in U1 plus U2, which means I have to somehow sort it out into a piece that's in U1 and a piece that's in U2. Well, how do I do that? Just distribution property, right? AU plus AV. Well, AU is in U1 because U1 is the subspace. Subspaces are closed under scalar multiplication. So if U is in U1, then AU is in U1. And also AV is in U2. These both hold because U1 and U2 are subspaces. But that implies that this has the form of something lives in U1 plus something lives in U2. So AU plus AV is an element of your closed under scalar multiplication. So you should see it's like the same kind of argument over and over. We're leveraging the fact that we know that these are subspaces and taking advantage of their closure properties. All right? Yep.
You just have to do these, three kind of simple steps.
Yep.
To show the subspace. Also implies the vector space.
Yes.
Why is the definition of vector space so complicated?
So the reason that, because you have to start somewhere is the thing. You have to have some sort of overarching space where all these things live inside. And then basically mostly what people do is they use the definition of a vector space to set up these big umbrella spaces that contain interesting ones. So as soon as I say Rn is a vector space for all dimensions n, then you only have to work on subspaces forever after. If I say the space of continuous functions is a vector space, and that means you can work for differentiable functions, twice differentiable functions, 3 times differentiable functions, increasing functions, and even functions. You get all that for free, where you can just use these properties instead. But you have to give yourself an envelope to work in, and that's what the big definition is used for. Okay, now the weirdest part of this argument is not the fact that this combination of things is a subspace. It uses the word smallest in the proposition. So the proposition actually says in the book that U1 plus U2 is the smallest subspace that contains U1 and U2. All right, and the sums of elements of that form, right? This word of smallest shows up. So I'm going to write down the way that Axler writes this down. So you can see how strange this looks, because this is not language you normally see. This idea of smallest. How many of you actually saw what it meant to be a smallest space or a smallest set in your 248 class? One person has any idea what that means. Can you tell me what it meant in that class? All right, there you go. Okay. So what we're going to do is, what I want you to think is there's 2 different ways of imagining what it means when something is the smallest set, right? A smallest set could mean that it lives in the intersection of every single set ever that satisfies that property. Or it could mean if you write down any other set with a property that the thing you're interested in lives inside of it. Okay, so that might be confusing. I'm going to make it more clear. Hopefully it will become clear because this is the first time we've seen the idea of smallest in here, but smallest is not going to go away. So the proposition says the following. Proposition U1 plus U2 is the smallest. We're going to talk about that word. It's the smallest subspace of V. Containing 1 and U2. And that means this has a precise mathematical definition, which I want to lay out before we do the proof so you understand why we're proving it the way we are. What I would mean by that is if you have any other subspace, if U is a subspace containing U1 and U2 implies that U also contains U1 plus U2. That's what we mean by smallest. then U1 plus U2 is the smallest such space. In set bracket notation, what we're saying is here, you've got U1 and you have U2. Those, if we can show that those are contained in U1 plus U2,
What is that last one?
spaces, sorry. So basically, logically, what we're going to do is this. We're going to show that U1 and U2 are contained in U1 plus U2. That's pretty trivial. And then we're going to say if there's any other subspace that contains these, it also contains this. The idea here is if U contains U1 and U2, then U also contains U1 plus U2. So U1 and U2 live inside the sum, and also any other subspace you can write down that contains U1 and U2 also has the sum living inside of it as well. That's what we mean by smallest. U1 and U2 live in the sum, and anything else that contains U1 and U2 as a subspace also contains the sum. So U1 plus U2 sort of is at the bottom of all spaces that contain U1 and U2. If you don't like this, you can think in the background, there's an idea of you're intersecting all subspaces. Containing U1 and U2. That's the other way of thinking about what the structure of this argument is, right? Okay, now I admit, I think that this is like not given the attention that it deserves in the book, because I think the idea of thinking about something as the smallest without having it and somebody logically explain to you what that means is a little weird, right? But this is what we're going to do in this argument. In step 1, we're going to show that this is true. And in step 2, we're going to show that this is true. Any other subspace containing U1 and U2 must also contain the sum, which you should believe is probably going to follow by closure under addition. Okay? Okay, so first, U1 is contained in U1 plus U2 because this is every U in U1 can be written U plus 0. And U plus 0 is an element of U1 plus U2. Because we're thinking about this as being an element of U, and this 0 right here, this 0 is an element of V. Or sorry, U1 and U2. Okay. Now this is the sort of formalism that can be confusing. All we're saying is anything that is just in U1 can be thought of as being in U1 plus U2, because anything over here could just be written as U1 plus or U plus 0. Okay. Also, by the same argument, U2 is contained in U1 plus U2. So U1 plus U2 is a subspace that contains U1 and U2. That's where we're at right now. U1 plus U2 is a subspace, which we just proved, that contains U1 and U2. Now let U, I guess we get a different letter here, W, be a subspace of V with one living inside of VW and U2 living inside of W. Makes sense? I'm picking an arbitrary subspace now that contains U1 and U2. I'm going to show that the sum also lives inside W. Make sense? Okay. All right. There's my smallest argument here. Okay. So how are we gonna show that it contains any element of U1 plus U2? I gotta do something, but I wanna show, I want to show a line in here. So what I wanna show is that W contains U1 plus U2. How do I show that one set contains another set? Yeah, pick an element in here and show that it's also an element of here, right? If I can show that any element of this is also an element of that, then I'll have one. I've got my subset containment, right? So we're gonna let U plus V be an element of U1 plus U2. Where U is in U1 and V is in U2. If U is in U1 and V is in U2, then that means U is in W and V is in W. Because we've assumed that U1 is in W and U2 is in W, and that means the elements that in them must be inside W as well, right? Okay, so what can you say about U? If U and V are both in W, what can you say about U plus V? Well, it must be in W. Why is it in W? W is a subspace, right? So that means U plus V is in W because W is a subspace. So what you just proved is that if you pick a random element, an arbitrary element from U1 plus U2, it's also an element of W. And that means you've proved that U1 plus U2 is a subset of W. So U1 plus U2 is a subset of W, but that's exactly what we were trying to prove. That means that U1 plus U2 is the smallest. Any other subspace containing U1 and U2 also contains U1 plus U2. And that's the conclusion of the argument. So U1 plus U2 is inside any subspace containing U1 and U2. Well, that means it's the smallest. So U1 plus U2 is the smallest subspace containing U1. Okay, I'm not harping on this because I think that there's like a deep idea here. I'm harping on this because this idea of being the smallest, this idea of proving it has a property and anything else that has that property contains it. That's an idea that we're going to see multiple times in this class, the idea of being a smallest set. Okay. This is the sort of argument structure that like it takes a little time to get used to. But when you're showing something as the smallest, this is what the arguments look like. It has the property and anything else that has the property contains it. You can use this to define a notion of biggest as well. All right, I think that is probably what I've got time for today. So where we are right now, when we handed, so what we're finishing here is, so we finished the idea now of set sums, right? And what we've shown is that set sums make subspaces, but they're not the most efficient subspaces because the argument that I put up on the board at the beginning of the class says that if I have two subspaces that add up to a bigger one, I'd really like to be able to say that everything that occurs in the sum can only happen one way. I don't want to be able to say these two vectors add up to this one, and also these two vectors add up to this one, and also these two. We use a coordinate system that we don't want that. If I say the vector 2, 3, I literally want 2 times this vector plus 3 times that one. I don't want to have some other combination that also gives the same thing. Multiple ways of adding up to 0. That's terrible. This is related to the idea of linear dependence. If you remember your 206 class or your earlier linear algebra, linear dependence had all this slop in the sets of vectors, right? And so we're going to introduce the idea of direct sum so that we can avoid that mess of having multiple representations. So we're building towards coordinate-like structures. So next time we'll talk about direct sums. You should read that part of the chapter. If you've got questions, so read this proof. It's not laid out like this in Axler, but it's the same argument. Okay. And then if you want to read for next time, read about direct sums. Because that was, we didn't start with the subspace there. Our sets when we started with in that case weren't actually subspaces. So the whole point with it, when you say a subspace, you've got all this extra information because all the possible linear combinations are also automatically. So you're never gonna have a subspace that's just like one element or two elements. A subspace will always be a whole bunch of additions already all piled up and ready to go. So there's basically no way to set that up in the context of subspaces. Yeah, you're always gonna get these sort of linear combination things.
We
going in the
just, it's
background.
kind of like state theoretic.
It has to,
Okay.
yeah.
I have a question about the homework.
Please.
I had like little stars
So the stars were because I hadn't talked about the materials needed yet. Those will be due next week.
for next week.
Yeah.
So
Don't, you can work, I left them in there so people can work ahead if they want, but that's not required at the minute. Going on.
Thank you.
Sure.
Yeah. What type of thing?
Yeah, I've heard a couple of positive comments so far, so.
I'm going to tag that, right, want to show this.
Yeah,
That's
no.
where they're going.
Yeah, I mean, I didn't, that's good because yeah, this is the sort of like giving yourself a hint so you don't get lost. Like, oh my God, what was I trying to show? Oh, there it is right there. That's the thing I was after. Yeah. Ooh,
When are you gonna post that?
tonight.
So the problem thing start, are we covered?
We have not talked about direct sums yet, and I think that those exercises may not require direct sums. You should be able to start them
Okay.
if you want to, but I'm not gonna have them due until next week. Why am I recording myself talking about this?